Okay, let me share my screen for folks on Zoom. We'll get started now. All right, so we're gonna first lesson of today is parallelism. So let's enjoy one of our vintage memes from 6 years ago of parallelism. And this is kind of the theme of the lesson, actually. The theme of the lesson is keep your parallelism as simple as possible. And sometimes the answer is to hire a bunch of summer undergrads to solve the problem. So we're going to talk a little bit conceptually about parallelism, and then we'll do some examples on in Python, and then we'll kind of go back and talk a little bit about big picture again. Um, what is parallelism? Parallelism is trying to harness. I'm going to make this text a little bigger. Go. Parallelism is trying to harness your computing power to the max. So most modern computers, we don't have just like one one core anymore. All your laptops have multiple cores. A lot of laptops nowadays have like 8 cores, 10 cores, 12 cores. Each core is a processing unit. So like if you're running a regular Python program, you just do a Python, and that program just does some stuff like NumPy, whatever. You're generally only using one core. So you're not utilizing your computer's full processing power. So sometimes, if you really want to make your code faster, one of the ways you could do that is by using the full processing power of your computer. Generally, think about parallelism in terms of CPUs. Now that GPUs are becoming more popular, there's also parallelism on GPUs. GPUs are kind of designed in a very different way. There's a lot more cores on GPUs. You can see some GPUs have like 2,000 cores. Each core can do less things, so there's a less capabilities that it can do. Your CPU can do a lot of things that your GPU can't do. And your GPU core generally have less things like less memory that it can access and things like that. So it makes it a little bit more difficult to program in some ways. But we'll hear about JAX after this, which is a one way to run things on a GPU in a pretty fast way that doesn't require a lot of technical understanding of GPUs and GPU debugging. GPU debugging is very hard because if you're really doing like low level GPU programming, if you crash your GPU, your entire computer screen disappears because your computer screen also requires your GPU to display things. So, but well, today for the parallelism lesson, we're just going to talk about CPUs and how to utilize your CPUs to the maximum. Many codes and algorithms in astronomy can be categorized as what's called embarrassingly parallel. This is a technical term. This is not a term about whether how good your algorithm is or how bad your algorithm is. It's just a technical term, meaning that it can be easily split up into multiple tasks that each have little or no dependency on each other. You can think of this as like, oh, um, I have a data reduction pipeline that needs to process 1,000 images, and I can literally process each image separately like 1,000 different times. Like I can have 1,000 pipelines and each process one image. That's an example of an embarrassingly parallel task. These are the tasks that we often encounter in astronomy. Um, uh, and um, yeah, so being able to run all these tasks at the same time is basically parallelism. One thing you're gonna completely see this in Notebook multiple times is that parallelism adds inherent complexity to your code. It makes it harder to debug and maintain substantially, I would say. So it's important to consider what the relative gain of implementing parallelism is versus the extra effort of in developing and maintaining that code. For that reason, we generally only recommend you parallelize code as simple as possible, and also only parallelize the tasks that get the biggest speed up from parallelism. Beyond that, you're going to run into more and more technical issues, and because you're making your code more and more complex to be parallel. Um, okay, there's some import statements. I'll just run these now, get these out of the way. Um, okay. There's a lot of gotcha, a lot of things. Okay, before we begin with multiprocessing, which is the module in Python we'll be using to do parallelism, there's a few kind of conceptual points technical points to get at. They're technical, they're not really conceptual. One is that only one process can spawn other processes. So the how parallelism is going to work is that we're going to basically create a bunch of different processes, give them processes a bunch of different tasks, and they're all doing them simultaneously. Like each core is doing something. Each core is running a process, is doing a different task, and they're all going to complete in parallel. And then we're going to gather up all those tasks, and hopefully that'll be much faster than one CPU doing each task one by one by one by one. Um, in general for parallelism, only one process is allowed to spawn other processes. So you can't have like a hierarchical pyramid scheme of parallelism. It can't be like this one process spawns five processes, which then spawns 10 processes, which then spawns 50 processes, and so on. Um, only one process, what's a technical term, your sub processes cannot spawn their own sub processes. This is generally how these operating systems are designed. And there's basically always a way to write your code so that only one process needs to spawn sub processes. You generally never need to be in a pyramid scheme hierarchy of processes all the way down. Um, Python is generally an OS agnostic language, which is very nice. People are here running on Windows, on Linux, on Macs. Um, Parallelism is one of the parts where the it starts mattering which operating system you're on, and you can run into OS specific issues as multiprocessing because it behaves under the hood. Things behave differently. The ways we're going to recommend you how to do it keeps it OS agnostic for the most part. The one thing you'll run notice is that for Mac and Windows, because of how threads versus forks versus I forget now how forks work and how basically how you create subprocesses in Macs and Windows work. Any lines with multi-processing have to be wrapped in this very like I don't know, obtuse if underscore underscore name underscore underscore equals parentheses underscore underscore main underscore underscores parentheses. You just got to wrap it in that. Otherwise, you're going to get an error that has like something freeze support something, and you're like, what is this thing? And the answer is you didn't wrap your parallelism code in that. Um, this is not required in Jupyter notebooks. I think. I don't know if this is true anymore. Anyways, we're gonna basically today, in addition to this Jupyter notebook, I've also put the code in individual Python scripts on the Code Astro repo, so you can run them on your computer in those Python scripts, and they'll have like the if name equals main wrapping in them, so you won't run into any issues. Hopefully, I don't have a Mac, so I haven't tested on that, but it works on my computer at least. Um, you really don't want to know the details for about why, but if you really do, there's a link to know why. One of the important things to do when you are running parallelized code is to check your resource usage using something like a task manager or something that kind of tells you your CPU usage. That kind of tells you, makes sometimes you're running parallelized code, you're not sure if it's really being parallelized. You can check by seeing how many of your cores are actually processing things. That's good way to check that you are actually successfully parallelizing your code. Another kind of thing is that parallelized code often uses more memory, so it's also good to track your memory usage because sometimes if you don't pass things in the right way, you might cause big pieces of memory to be duplicated, which will cause your memory usage to potentially be much bigger than you think, and maybe your computer will run out of memory. So this is important things to do. All right, so we're going to learn about how to do parallelization in Python using one particular kind of high-level parallelization API that it offers, which is called pools. Pools is basically a like a list of not a list. It's like creating a bunch of worker processes that are just waiting there, sitting there waiting for tasks, and then you start giving it tasks, and it'll start doing those tasks as it receives them. And basically, all the kind of synchronization and how to handle these different worker processes is done underneath the hood, so you don't have to worry about it. Um, Manually creating processes and doing it yourself is doable. I have a lot of experience in that actually, but I highly do not recommend ever doing that. It is prone to errors and really tedious. And generally we try to, in the spirit of our recommendation is always to keep parallelism simple. So we always when you're using a language, figure out what the high level API exists for handling parallelism is and use that high level language because uh, unless you generally never want to be using very low level parallelization in a language. That's true, there's almost no cases in which you probably want to do that. And for Python, my kind of thing is when in doubt about how to parallelize code, I use process pools. The thing I'm going to show you here is basically how I do parallelization almost exclusively in Python. Um, and they are very flexible and they can accommodate most use cases. They have a very standardized use interface for them. So let's just take a look. So here we're basically going to, I think, do matrix dot product, but we're going to manually split up the matrix dot product. You know how matrix dot product, you're taking like a row times like of one matrix times the column, the next one, the row of one matrix times the column, the next one, et cetera, et cetera. You can kind of break that up into tasks, right? Like one task can handle like this column times all of these rows, and then another process can handle this column times all of these rows, and one column could be like this column times all of these rows. So you can break up matrix dot product into a parallelization thing. Actually, NumPy does this under the hood. So if you install NumPy with Conda, it automatically parallelizes your matrix dot product. But we're just doing it by hand. We're doing it like ourselves here, just as a demonstration. So I have, you guys can read this. Is this too small? Let me make this bigger. Okay, let's make this bigger. So we have a matrix. We'll make a big matrix, 8,000 by 3,000 matrix. And then this little function is basically just doing we're dividing this matrix dot product into 10 different jobs. And each call to this with the index parameter between 0 and 9 does 1/10 of that matrix dot product. It's a very clunky code. Okay, it's just for the purpose of demonstration. And how we're going to do this, like you would have to wrap this entire block normally in like if name equals main, basically if you're running it on like Mac and Windows. What we do is we create a pool. I created a pool with 4 processes. So there's kind of 4 worker processes sitting there waiting for things to do. Remember, we have 10 jobs. So these 10 jobs are going to be distributed to 4 worker processes. What's going to happen is that for each of those 10 jobs we want to do, we run this command called pool.apply async. Apply async is basically creating a task for this pool to run asynchronously. And this task, the first argument is the function that you wanted to run. So matrix pool is this function we just defined. And the second argument is the arguments of that task that you want to pass into. So we're passing an index telling you between 0 and 9, which part of that matrix are you in charge of parallelizing. So you want to always have some sort of argument that indicates, what part of this job are you in charge of doing for this particular task. And this outputs basically a task object. This is an object. This is not the answer. This is not the return value of the function. It's just a task that you can eventually obtain the return value of the function from. And we can basically append to a list all the tasks that we have created and put into our pool. So we'll create 10 jobs. And then after we create those 10 jobs, we're going to basically, for each of these jobs we just created, for each of these tasks we created, we're going to use task.get. And this will get the return value. The return value only exists when the function has finished running. So your main process as running task.get will just sit here and wait here until the worker process finishes that task. If you try to grab that first task, if you try to say like you create 10 tasks, you try to grab like the 9th one first, you're going to be sitting there waiting for a while because you're probably the process is going to pool is trying to probably run first task, second task, third task, fourth task, all the way to the 9th task before that task finishes and returns, and this function actually returns. So your main process can hang here for a while until it gets the return value. And then this result is the return value of calling matrix pool with this argument. So it's like a 2-step process now to get the return value of that function. And at the end, you always want to call these commands pool.close, pool.join. This will make sure that all the workers have finished and they're kind of idle, and you close your pool, which will clean up all your workers because those workers have a lot of overhead if you don't clean them up. Okay, we have some questions. Okay, I think I saw your hand first.
So the point is you're applying this asynchronously, so any task can finish at any time, right?
That's correct.
When you use enumerate, are you forcing it to be synchronous anyway? Because it just goes from the first task in the job to the last one.
Not necessarily, because some tasks can be longer than others. So the question is, because this is asynchronous, but because I'm doing it in a for loop, doesn't the first task always finish first, second task always finish second, third task always finish third, and so on. I mean, it depends on how long each task takes to run. So task 1 might take 1 second, task 2 could take 100 seconds, task 3 take 10 seconds. So like there will be they will be the worker processes will grab them in order that you put them into the queue. But when they finish depends on how long each process will take.
Yeah, but you could be stuck on like the second task while all the rest are finished, right? But you only have two iterations of your loop. That's how you're doing it in Enigma, right?
So the question is basically we'll be stuck here. If the second task takes forever, we'll finish task one and we'll get stuck at task two forever until that finishes before we get the rest of the task. That's correct. That's how we wrote this, and that's how long it will take. But generally, when you're doing parallelism, you're always going to be limited by your slowest parallelized chunk. So that that's that's not inherent. That's not an inherent weakness of this paradigm. This is just inherent. That's just how parallelism will always go. I think I saw your.
Yeah, so like you create the jobs by
Mhm,
doing this apply basic,
mhm.
and then you assign jobs with tasks. Is that correct?
So the question is, what is applied async doing and what is task.get doing?
Yeah.
So applied async is putting, like you have a process pool that's kind of waiting for jobs. Applied async is giving jobs to that process pool. And once that job is there, they'll start working on it immediately. The task.get is to get the result. So like between this line of code and this line of code, that process pool is already starting to process your jobs. And if they are really fast, they could have finished all of the tasks by the time you even got to here. But if they're not that fast, you'll be waiting here until they finish their jobs. Yeah. That was another question.
Was test subject is pulling one answer at a time.
Mhm.
How is this parallel? Because it looks like it's sequential, but from what I understood, all of the tests are being run at the same time,
Mhm.
but when it comes to pull the result, that's
Mhm.
sequential.
Yes.
Pull the result first one, second, but everybody's running it.
Yeah, the question is how is this sequential and how is this parallel if it seems like we're just getting results sequentially? That's right. The kind of the leader thread that's kind of maintaining this is obviously can't parallelize itself, right? It has to do sequentially. It's just that like you said, after we run apply async, all this other stuff is happening in parallel separately in other processes that we don't see. And they are returning whenever they're done. And but the main thread that's kind of the thread in charge of coordinating all of these has to operate sequentially. There's no way to program any one thread to not obey time ordering of its commands, but we're just running commands on other processes that are happening under the hood that you don't have to see here. We could program a bunch of processes and write out the code for what they should do separately. I just highly recommend you never do that because it is extremely painful and it's very easy to get it wrong, actually. Um, and getting it wrong is very hard to debug. Um, okay, let's see how this works. So notice anytime we create a job, we'll have a print statement that job is created. Anytime in matrix pool, we finish doing a bunch of matrix algebra, we'll get a job complete from the worker thread. And anytime we get a result, we'll get a print statement that we got a result. So we have there's three stages. We put in a job, we complete the processing, and then we get the results. All right. Live demo. What can go wrong with parallelism? Okay, so we created all 9 jobs. You see all that happen. Oh, jobs 1, 0, 2, 3 complete. The thread, got get on 0, 1, 2, 3. Job 4, 5 complete. We got the gets on 4 and 5. 6 and 7 complete. We get the gets on 6 and 7. 8 and 9 complete. We get the gets on 8 and 9. So you can see that, in some cases the processes are completing the jobs asynchronously, but the nice thing that you don't have to worry about, trust me, that you definitely don't want to worry about this, is that you get the jobs back in order serially, like you are not running things in parallel. And that's actually a feature. You don't want to have to think about if your things are finishing asynchronously in different orders, how do I then figure out the right order for everything? You might think it's simple for a simple example like this, but it just gets more and more and more complicated. And the edge cases are very painful. So that's all handled under the hood. So you don't have to worry about that. You just get all the jobs. Like you can see the jobs finished asynchronously, but you get the results 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So that's apply async. I basically, like I said, use this almost exclusively. There is another alternative in the multiprocessing pool API, which is called map. And you can basically map a function to do a bunch of different things. And it has also some alternate flavors called IMAP and star map. I personally find this to be less flexible. So I don't really use it very much. I basically almost always use apply async because this is very intuitive to me. You just have a pool, you have a bunch of jobs you want to give it, and you're just giving it jobs with every time by running apply async. Never run apply. Apply doesn't parallelize your code. I don't know why they have that function in that API. It's a trap. Okay, another question?
Before, what's the different use cases for apply async versus map if one's flexible?
What are the different use cases between apply async and map? Map comes from it comes from more of a mathy background. It's thinking about really distributed computing on very large scales where you want to break up a task across many different cores. And there's a algorithm called map reduce, which is basically how do you take some sort of problem, distribute it into a bunch of cores, solve them asynchronously, and then bring all the results back to give you your final results. And this is something called map reduce. It's used quite often in cloud computing. You might it's kind of backbones of things like Facebook and all these other services that you run in the cloud, especially things that use databases in the cloud. It's just very complicated. It just adds more layers of complication that just like makes me require thinking more. And apply async is very intuitive, basically. And they give you the same answer. And basically, I haven't found a problem in astronomy where I have to use map. I basically can always use apply async, and I can then understand the logic in my own terms rather than understanding it in this like very mathematical map plus reduce framework I find to be more restrictive. Okay. All right. So you're gonna get some experience doing this. So we're gonna do a image processing activity. So your goal is to basically we're gonna generate some fake data and then run some fake image processing on it, and then you're gonna document, how long does it take to process the data with one core versus how long it takes for if you parallelize it with multiple cores. So we're gonna generate 20, so there's a cell here below that basically generates fake data or generate 25 fake frames of data. Let's just run this and see what happens. And after you generate those 25 fake frames of data, there's going to be a second cell that has a single image processing step that we want to run on each image. So we want to run this step on each image once. The function is called process image. And it takes a little bit of time to run on each image. And here's an example of it running on a single image. We'll time it as well. It takes maybe about 15 seconds to run, maybe. So your goal is like, I give you some example code for how to run it on a single image. We also time it on a single image for how long it takes. Your goal is to parallelize it, to process all 25 images in parallel and figure out how long it takes to compute, how long you're able to speed it up by processing it in parallel, and then compute the speed up factor, between doing it in parallel versus doing it serially one image at a time on a single core. And then if you are successful in doing that, try using different number of processes in your process pool. Try 2 processes, 4 processes, 8 processes, 32 processes, 100 processes. Do you at some point hit hit a ceiling, and see and how does that relate to the number of cores you have in your computer? And do you actually get a linear speed up as you use more and more processes in your process pool? So in the end, you can report on Piazza the speed up factor as you get based on how many processes you use and how many cores you have. And if you have really a lot of time, make a graph of the wall clock time it takes to process 25 images versus the number of processes used in your process pool that you create. You can post this on Piazza as well. Let's do this in groups. If you're around with your project groups, do it with your project groups. Use your normal pair programming setting. Oh, here it took 27 seconds. And you can see this is our original image, and then this is our process image. So we're going to do this for 25 randomly generated images. You can see that the images get randomly generated here. There's like 25 of them. Just like one other logistics. So we're gonna be in the day 2 folder of Code Astro in the parallelism folder, and you just want to there's the parallelism notebook here, and if you want, I've put this all into the image processing.py file, so you can just run this file. It will right now just generate all 25 images and then process one image and time it sequentially, and then your activity is to in this if name equals main, probably make this into a parallelized piece of code and see how fast it takes to run. Okay, so what time is it? It's 26. So uh, let's come back at 46 minutes after the hour, so 20 minutes from now. Let's give it a shot, see how it goes, and then we'll recap and I'll talk about a few more parallelism things at the very end, which is just a giant rant, I think. But okay, let's break for the next 20 minutes. Okay, everyone, let's get back together. It seemed like people were making some progress, but you can tell that parallelism is tricky. Some of you maybe ran into some really weird bugs about what's going on. This is a taste of parallelism debugging, where it's sometimes quite hard to kind of reason through when there's multiple processes running at the same time. How did this error message come about? Because sometimes it's like one process running a bit faster than the other, causing an error. One process running a little bit slower than the other, causing an error. So this is sometimes these bugs only appear randomly. We call them Heisenberg bugs because they only appear when the certain state it happens. This is a taste of parallel, and this is the simplest parallelism kind of structure there exists, basically. And the more complicated, you'll just run into more of these bugs. This is why we recommend to kind of keep things simple. Let's see. I think I saw some folks get really close to get to the answer. Yes, so we got some answers. People were able to do the entire processing going from 203 seconds to 37 seconds with 13 cores, getting a 5x speed up, going from 200 seconds to 52 seconds with 10 cores, getting like a 4x speed up, going from 229 seconds to 19 seconds with 16 cores, getting about a 12x speed up. You see that the speed up you get isn't exactly equal to the maximum number of cores you have. There's always some inherent overhead in parallelism that you never quite reach like pure peak. Like, you can think of it like if you had 4 cores, you think the best speed up you can get is 4x, right? You go from 1 core to 4 core. But because of some inherent overheads, and other kind of complications, you never quite reach that exactly pure 4x. So you're always a little bit under, and there's always the work to do to get closer and closer and closer to it. It gets harder and harder and harder. But this gives you a little bit of taste. Seems like some of you were successful. I'll post the answer keys to this afterwards. But it was basically trying to, like you guys were trying to do, copy that structure and putting it here for this particular activity. And if you had trouble running on your own computer, right now, at least of this lesson is working on Colab. So try opening the notebook in Colab with the answer key, and you can try to run it on Colab in the Jupyter notebook with the answer key. Okay. How much time do we have? There's a bajillion things in here. We have 5 minutes. Okay. Parallel debugging. The recommended debugging strategy of parallelized code is to get it working on non-parallelized code and then wrap it in parallelism. Debugging parallel code is really complicated, and you basically really you should be asking yourself, can I do this all without doing the parallelism first? And then basically make sure your function is working as intended, and then debug the parallelism structure afterwards. You have the function working as intended. Yes, separate those two things. There's a lot more ranting about parallelism that I have here. I'll just point to a few things. One is, do you really need parallelism? You guys have experienced that, it takes quite a bit of work to get the parallelism working. It's quite complicated. Even though the number of lines of code you're actually writing is not that much, getting it to work and understanding how it works is not particularly easy sometimes. So basically try to avoid parallelism until it's absolutely necessary. If some code takes 10 minutes to run and you only need to run it once a week, is it worth parallelizing? It's a really legitimate question. And the upkeep cost may not be worth it. There are some easier ways to parallelize than just like one way to parallelize is literally open 10 terminals and run that script 10 times on each of those 10 terminals. That is a parallelization strategy. I do it sometimes, and it sometimes works just as well as trying to do all this multiprocessing stuff. Um, there's also a command line tool called GNU parallel that basically is the same, that you want to run, open up 10 terminals and run this thing on 10 different files. There's basically a way to parallelize that on the command line without having to write your own parallelism on top of that. The pain that we must all suffer to do parallelism in Python is 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 unfortunately inherent to Python for now. Um, there is a much easier way to do parallelism if we could use threads. So there's in Python both a multi-processing and multi-threading library. Threads and processes almost sound like the same thing. They're both things that can run on other cores, and you can create pools of them, and they could be worker jobs, worker things that goes out and do things. Unfortunately, for this thing called the global interpreter lock in Python, for CPU, for things that require computations on a computational bound task, things like require lots of computations, you can't run multiple things at the same time. Only one a thread can ever run in a process at the same time due to this thing called the global interpreter lock. Um, I'm not going to go into it in more detail, but in other languages, you can use threads instead of processes. There's a whole kind of comparison between threads and processes. And if we were in a different language that didn't have the global interpreter lock, maybe Python in a few years, they're thinking about removing it, but apparently it will break a lot of parts of the code before they get there. If we can get that, we'll be able to do much easier parallelism. Some of it will be less clunky, and it might also it will be yeah it will allow us to do more things than just it'll make things easier in general. But we are basically not there, and because of that, we're stuck with this thing called multiprocessing. And multiprocessing, I guess I'll give you one taste of why it's hard. Um, Processes, unlike threads, do not share memory. So if you want to process a bunch of different things, to pass data between memory, different threads can share the same memory. So if you define some variable A, all the threads can see it. Um, if you define a variable A for a process, none of the other processes see it. You have to explicitly declare a chunk of memory at creation of all of your sub-processes to be shared. And these are the things that we're sharing between those processes. And you have to declare that all ahead of time. And because of that, inter-process communication is kind of clunky and difficult. And it creates a lot of these bottlenecks, and why multiprocessing and apply async are the way they are, and why we are basically telling you just do this, don't think about anything else, because it just gets more and more complicated if you think about more things. If we didn't have the global interpreter lock, and we could use multi-threading for computationally bound tasks, we could get rid of some of these things. But that's a rant for another day. And shared variables is also a rant for another day. But if you're interested, I have all this stuff written down. It's a little bit ranty because I kind of just written down as I decided to, as I was thinking about it. But hopefully it'll give you some insights if you want to dive more into Python parallelism. But for almost all cases, opening things on a bunch of terminals, running them in parallel, or multiprocessing apply in sync should hopefully get you most of the way. Okay, I'll take one question and we gotta move on. What question do I recommend to use parallelize? I only use Python, so I just suffer through whatever Python has for parallelism. Don't worry, there are other languages with worse parallelism than, sorry, not worse, clunkier parallelism than Python in many ways too. So there's pros and cons to various parallelisms. But it is what it is. And I don't think there's there are probably better languages, but I don't program in them, so I can't recommend one.
Most of what we have to do for astronomy, there's really no reason, like Jason was saying, to like get into the weeds of like actual like worrying about threads and shared memory and stuff like that. If you're working on like, like if you're programming like a satellite that's going to go into orbit and it has limited resources, then like limited computational resources on board, then that's a situation where like you probably don't want to use Python, just because like, compiling and running objects is just going to be hard. So you might want to use a lower level system. And if you do need to use parallelism, then worry more about those things. But for a lot of our day-to-day tasks, we don't really need to worry about it.
If you're coding up operating systems, you have to worry about this a lot, but I don't think any of you guys are.
Yet.
Yes.
No.
Astronomy operating system. Okay, let's wrap this up here, and then we're gonna do JAX next.
You want to take a 5-minute break?
Let's do a 5-minute break. Good idea.
Okay. All right, everybody. We're going to get started with the JAX lesson. Yeah, this is a really brief introduction to JAX. JAX is something that's it's a Python package, but under the hood, it operates very differently from Python. On the surface, it looks very similar to NumPy code, but when you get into what it's actually doing, it's actually pretty different, but it can help you speed up your code a lot and also take advantage of GPU programming fairly easily. So the main features of JAX are it has XLA compilation. So I'm going to talk a little bit more about what compilation actually means in a second. But basically, JAX under the hood is compiling your code very efficiently using this linear algebra library called XLA. It also has, it integrates pretty seamlessly with GPUs and also TPUs, which are essentially GPUs. And so you don't have to write any special code in order to run the same code on a CPU or a GPU. So if you ever learned like CUDA, for example, there's like very specific syntax and very specific libraries that you need to learn in order to run your code on GPUs. With JAX, you don't need to do anything special. It will detect that you have a GPU and it will automatically compile and run your code on the GPU. JAX is also equipped with automatic differentiable programming. So if you need gradients for anything, so for example, if you're running a gradient-based minimization algorithm, or if you're running a Hamiltonian Monte Carlo, MCMC, those things all require you to know the gradient of your objective function. And so if you don't want to calculate that or you can't calculate that analytically, being able to do this within JAX is very helpful. Okay, so I'm going to tell you about just-in-time compilation and talk about compilation in general, give a few examples of how JAX works, and some of the sort of unintuitive bits of JAX. If we have time, I'll talk about the jax.grad and jax.vmap functions. These are basically just two useful things to know about, but you can also read them on your own. And then we're going to do an activity of running JAX on GPUs and looking at performance improvements, actually using the JAX compilation, and then seeing compiled versus not compiled, how that changes the performance, and then also on a GPU versus a CPU, how that changes the performance. So I've had this meme up for a while, but we can appreciate this meme, and yeah, good meme. I like this one. All right, so we're going to start off with what is just-in-time compilation. So in general, in order to understand just-in-time compilation, you need to understand compilation in general. So compilation is the process of translating code that you wrote in Python to something that your machine can understand. So you're translating to machine code. Python is not a compiled language, which doesn't mean that compilation isn't happening. It just means that you don't have to run compilation before you actually execute the code. So if you've ever worked with like C code, for example, you might remember that there's a whole separate compilation step. So you compile the code and then you run that compiled version. Compilation involves a lot of error checking. So basically you're checking that like all of your like types in Python are compatible. You might notice if you run a Python code that has a syntax error in it, that error pops up very quickly. So like if you are missing a parentheses, for example. Whereas if you like have to actually, if you like have an attribute error, so if you try to access some attribute of a class that doesn't exist, it usually takes Python a little longer to actually get to that error and discover it. And that's because these errors are being discovered at different steps of the execution process. The syntax errors are discovered at the compile process, so that happens very quickly. It's the first step. and then attribute errors and other errors are discovered at runtime, so after the code has already been compiled and is already running. So just to review, Python still compiles your code, it just does it when you actually like run your code. You don't have to compile it separately and then run it. So JAX looks like Python code, but it actually optimizes the compilation process under the hood. So that makes it different from native Python. And it's also going to compile it automatically for GPUs. Like I said, if it detects a GPU on your system, it'll automatically compile it and then make it runnable on the GPU. It's important to note that although JAX's compiler is fast, it's not infinitely fast, and it's still going to take time to compile. So, for example, if it's not always faster to use JAX than to write normal Python code. And it's especially not always faster to run code on a GPU than it is on a CPU. It takes time to do compilation. It takes time to offload your process to the GPU itself and then take that result and pass it back to your CPU. So all of these things incur a certain amount of overhead that you'll also explore in the activity later. So the types of embarrassingly parallel programs that Jason was talking about before, like running, the same analysis script on 10 different images, are really not going to be conducive to JAX. JAX is really meant for when you have to do lots of matrix algebra on the same size arrays over and over and over again. It was written originally for training neural networks, but it's used pretty broadly nowadays. Okay, so how does it actually do this? JAX has this function called JIT, which JIT stands for just-in-time compilation. And the just-in-time compiler it has two steps. It first translates your pure Python function into this intermediate language that's called JAXPR, JAX expression. And then that JAXPR is then passed to this XLA library to be compiled. So XLA itself is a very fast compiler, but the additional layer of optimization that JAX does is turning your Python-looking code into this JAX expression code. So the way that JAX builds the JAXPR is this process called tracing. So basically, when you run your code, JAX attaches a tracer object to each attribute. Attribute is defined weirdly here, but never mind about that. And it will have this tracer go through the code with you and go through the code as your code is actually executing. And if it goes through a function with a given input, it will compile that into JAXPR and then compile that JAXPR into XLA. So if that function is then called again with the same type of input, it'll use the compiled version rather than actually running it in Python. So, okay, that's a lot of words. Let's see how this actually works. So here's some code. We're going to import JAX. We're importing jax.numpy, and then we're also importing numpy. We're not going to use numpy in this cell. We'll use it later down. So I've defined this add1 function, and I've added this jax.jit decorator. So that means that I want this code to be just-in-time compiled. I want it to be traced, and then I want if I encounter this function again in the future of my code, I want to use the compiled version of the code if it exists. So this takes in a jax.array object, and it returns also a jax.array object. So there's three things that are happening in this function. The first thing is it's printing the statement, I'm being traced. This is what's called a side effect in functional programming and in JAX. So basically a side effect is anything that the code does that isn't directly captured by the output. So if we were to run this add1 function, you wouldn't know just based on the value of this y that this print statement happened. So this is a side effect. There's sort of weird and unintuitive things that happen to side effects in JAX, which we'll see in a second. So, okay, the next thing is we define this new variable y, that's x plus 1, and then we overwrite the value of y to be 5 times x, and then we return y. I don't actually know why I did the y definition twice. I wasn't trying to make a point with that. Oh well. Let's take that out. We don't need that. Okay, so we're going to first call add1 a single time. And because this is the first time it's being called, it's going to trace this. This code. It'll translate it into Jaxper and then translate that Jaxper, compile that Jaxper with XLA. The second time, we're going to call it again with an array of the same shape, the same size. So this array just has one element, and then we'll see what happens. And then the next thing we're going to do is call it with an array of a different shape. So we're going to add one with an array that has length 3. So let's try this. All right. So here's the result. We print out the first call. You can see the print statement happens. I'm being traced. So the side effect happened here. We get our result. The second time, we don't get this I'm being traced side effect. The reason for that is because any side effects are not included in the compiled version. So this time, it's using the compiled version of add1. It's not actually doing the tracing again. It's recognizing, okay, I've seen this function before with this shape of input. I have the compiled version of this. I can just call that for a massive speed up rather than calling it actually in Python. Here, it's tracing again because we have an array of a different shape. So it can't use the compiled version because the compiled version assumes a particular shape. So we see the side effect happen again, which is our sort of our understanding that tracing was happening there. Any thoughts or questions so far? Mm-hmm.
Does that mean the print function is not compiled?
Yeah, so the question is, does that mean the print function is not compiled? It's a complicated question. So it was compiled in the version of the code that's run now, but it's not included in the compiled version of the function that Jax is going to then call.
So what determines what lines of code is included and what's not?
Yeah, so anything that's a side effect is not going to be compiled. So basically anything that doesn't affect the output directly is not going to be included. So the fact that, we could take this out and y would still be the same means that that print statement isn't going to be included in the compiled version. Yeah, great question. Mm-hmm.
So that means if you define a variable z equals x plus 1, that's not going to be compiled.
Yeah, if it's not included in the return statement. Mm-hmm. So if it does eventually affect the return statement, it will be included. But if we did just z equals 5, that won't be included in the compilation. It'll be optimized out. Yeah. There is a way that you can actually examine the Jaxper if you're interested. So there's some tutorials that I linked from the bottom here that will show you how to actually look at the Jaxper. Other questions? Mm-hmm.
Yeah, so let's just say you were to run this again on an array of size 1, does it still store that compiled version? Or okay.
Mm-hmm.
Because I was wondering if once you ran on array of size 3, if it deleted the other one.
Nope. Yeah, good question. Yeah, so the question was, if you were to run it again on an array of size 1, will it still use the compiled version? And that's true. It's storing all of the different compiled versions. It doesn't overwrite them if you run it with an array of a different size. Mm-hmm. Yeah, great question. So the question was, is it good practice to avoid side effects because it might get confusing knowing what your function is and isn't doing? Yeah, that's exactly true. In general, with functional programming, you want to try to avoid side effects as much as possible. That's one of the sort of tenets of functional programming. So Jax is a purely functional language. It doesn't do anything. It can't change. It's very difficult to change memory in Jax, which we'll see in. Mm-hmm.
Y is involved in that return. Do they keep that print statement as a non-side effect, or is that?
Say that again?
If you had a statement that said print Y,
mm-hmm.
would that be considered a side effect?
Yes, yeah, that would also be considered a side effect. So the question was, if you had a statement that said print Y, would that also be considered a side effect? And yes, it would still be considered a side effect because Y is not, this statement doesn't actually affect what the value of Y is. So these are all the sorts of things that the tracing process detects for you. So it'll detect anything that's unused and unnecessary to getting your output. And so that's one of the reasons why it makes it fast. It optimizes all of these things. Yeah, great questions. Thanks. Uh-huh.
If you were more concise programmer, you wouldn't have any lines in there that don't directly affect the output.
Mhm.
In those cases, does it do anything to optimize it?
Yeah, so the question is, if you were a concise programmer, you could take this out, and you might think that, like, does the compilation do anything other than just removing these side effects? So the main thing is that it's compiling it directly into machine code. So if you were to write this function in Python, or just using NumPy, like y equals x plus 1, return y. So every time you like run this code, it's not going to use a compiled version of the code. It's going to recompile this function each time. So you're using basically like a Python version of this, not a machine code version of this. So the fact that it compiles it directly into machine code and you can just access that makes it super fast. There's a lot of other optimizations that happen, but that's sort of like the main one. Yeah, it's a good question. So the question is, like, if you really wanted a print statement, is there some way that you could force it to print something out? I don't know. I don't.
You return y and w, and you.
Sure. You could return more things. So you could change the structure of the function so that you're actually changing the return type. So that would then affect the output. That would still be within the functional paradigm. Yeah. Yeah. I see. Good question. So I think let me just try to rephrase what you said, which is that one of the main advantages of JAX is that it integrates with regular Python code. So if you want to then, like, print the result of this computation, you can still, like, Python itself is not only functional. So you could say, like, we're printing the result of add one. So that itself is like a side effect of the whole Python like execution, but we can keep that happening. It's just things that are within this jax.jit, like functions that are JIT compiled won't have any side effects. Yeah, cool. Thanks, those are great questions. All right. Okay, so let's look at like one of the main motivations for using JAX, which is speeding things up. So let's examine like how long it takes to run this particular function with and without JIT compilation. So with JIT compilation, it's going to compile the function, and then it's going to use the compiled version of the function for all subsequent iterations. Without JIT compilation, it's going to, I kind of gave away the answer here, but whatever. Without JIT compilation, it's just going to call the pure Python version of this over and over and over again. Okay, so we've got this celu function, which you might recognize from machine learning, and we've got this. We're going to return, if x is greater than 0, we're going to return this function. If it's less than 0, we're going to return x itself. Then we're going to create this NumPy array, and then we're using this timeIt function. In Python, we're going to run 2,000 iterations of this command. You might notice this block until ready thing too, which is one other nice like speed up that JAX allows you to do is to continue executing code even when other bits of code are still like being executed on a GPU. So if we didn't have this block until ready statement, what JAX would do to compile this, to optimize this code under the hood, is to run this celu function on the GPU, so send all of this computation to be done on the GPU, and then keep running all of this like in our main instance. And then it will automatically populate the variables that it needs once it's finished. So that's really nice because you don't have to like wait for very intensive functions to be finished in order to keep like going with other parts of your code. The reason we have this block until ready here is because we're actually trying to time this whole like, execution. Okay, so we're first going to do this. We're going to run this celu command 2,000 times without JAX, without JIT compilation. And then we're going to run it with JIT compilation, and then we'll see what happens. So it's running, but I guess you saw before that with the JIT compilation, you get a pretty significant speed up than without the JIT compilation. All right, so we've got 873 microseconds per loop without the JIT compilation, and then 94 microseconds per loop with the JIT compilation. One really sort of funny / interesting thing about JAX is that when you run this time it sometimes with a JIT compiled function, you'll get a warning that says one iteration was significantly slower than the rest, and maybe that means that something's wrong with your code. So nothing's actually wrong, it's just the time it function recognizing that the very first time you ran this code, it did the whole process of JIT compiling, which took much longer. And then in all the subsequent runs, it was using the precompiled version, and so it was much faster.
What's the typical time to compile a small function like this?
I don't know the time off the top of my head.
Is it like microseconds, milliseconds, or seconds?
Yeah, I mean, given that it's I think it's going to be microseconds, something like that, yeah. Yeah, so the question was, isn't this not a super fair comparison because we're feeding JAX arrays rather than NumPy arrays? I don't think it makes a huge difference here. I'm not sure off the top of my head, but we can try. Yeah, I don't think it should matter. The JAX arrays are represented slightly differently than the NumPy arrays, but not different enough that I think it will significantly affect the runtime here. Yeah, it's not like they're much bigger objects, for example. Yeah.
The JAX version isn't getting a head start somehow by running it without JIT version?
Yeah, good question. So the question was, the JAX version isn't getting like a significant head start by by having this version run before the JIT compiled version. And no, it shouldn't be. We can change these around and it should be exactly the same. Let's just run it 200 times to make it a little bit faster. Yeah, so the JIT compiled version is still significantly faster than the non-JIT compiled version. We did get the warning this time too, which is fun. So the slowest run took much longer than the fastest run. Yeah, good question. All right. Yeah, okay, actually here, this is the exact answer to your question. So the important thing to note is that like the actual process of converting the function to JAXPR and then compiling it is going to take some amount of time. So you really only want to do this if you're going to be running the same function with the same sized inputs over and over again. So here we see the actual compilation time. Remember above it took like, 85 microseconds or something like that when we ran the JAX the JIT compiled version. But if we just run it one time, you can see it takes 255 microseconds. So that actual like compilation step is going to be pretty significant, even just compared to like running one version without any JIT compiling. All right. There are a couple of limitations for JAX code. One that's important to keep in mind, comes up relatively often, is that JAX fails when you're conditioning on an unknown variable. So if we're trying to JIT compile this function, we have this Boolean if x is greater than 0 in the conditional, then you return x, otherwise return 0. This is not going to work. JAX needs to know what the output is going to be like at compile time, so this code's going to fail. So one really nice thing about JAX that makes it very appealing, but I think also kind of like dangerous in a way, is that you can use a lot of the NumPy functions that you're familiar with. They have jax.numpy counterparts. So you can use linspace, for example, to create uniformly spaced arrays. There's trigonometric functions here. You can take means, medians, etc. All that's already implemented in JAX. So it sort of appears like it can just be a drop-in, replacement for all of your NumPy functions. But then it's important to keep in mind that you have all of these sort of weird effects, like you're not going to see print statements, and you might not actually get significant speed ups. You might get your code to be significantly slower unless you have, multiple matrices that you're going to multiply many times in a row. All right. I want to show you one more thing, and then I'll let you I'll let you work on the activity. This is sort of like a brain twister kind of thing. That's the difference between JAX and NumPy. So here we have a sort array function. So we're going to take in an array, either a NumPy array or a JAX.array, and we're going to sort this array using this r.sort, either with NumPy or with JAX. So we're going to print out the library name, the original array, and also the returned array. So first we'll run it with NumPy here. NumPy, if you run r.sort, NumPy sorts in place, meaning that like NumPy will go to the location in memory that you've got this array stored, and it will replace those elements with the sorted version of the array. So r.sort itself doesn't actually return anything. It happens in place, so it's a side effect that it affects the value of the memory where array is stored, and then it returns nothing. So you can see the output here is we get the original array, and then the return array here is none. So nothing was actually output from it. In JAX, you can't have any side effects. So this is another example of a side effect, like actually changing the value of something in memory. So this r.sort, this keeps the original value of r, and it returns an entirely new sorted array. So these types of things are important to think about because you could, very easily get like messed up if you have some NumPy code that you expect to have, side effects, and then you run it using JAX, and then you don't actually see your side effects come up at all. I'll let you guys read through the rest of the, actually I want to talk about this one because this one's really confusing. The last one is that JAX sometimes doesn't want to raise errors because actually raising an error from a GPU is very difficult, so it'll do a lot to avoid raising errors. One sort of very unintuitive example of this is that JAX doesn't raise out of bounds errors for arrays. So here we're printing out the 11th index of an array with only 10 values. And it doesn't throw an error, it just gives you a value. It says, oh, the value is 9, which the value is not 9. That's just whatever happened to be at that location in memory at that given time. So it's just nonsense. It doesn't mean anything. So it's important to keep that in mind. Do you have a question?
Yeah, so if you technically specify an extremely large number, does it eventually runs out of the RAM or the stack or whatever is the RAM of the computer?
I'm not sure. So the question was, if you specify an extremely large number and you run out of RAM eventually, what's it gonna do? What's the behavior gonna be? I don't know. You should try it.
It might depend on how you do a virtual RAM to physical RAM mapping, how that works.
Yeah, what he said. Yeah, so to avoid the specific behavior, you can set a fill value. So if it if you try to access a value outside of the limits of the array, you can say, okay, if there isn't anything there, just fill it with the value of 12. So then when we do it the second time, it'll say 12.
So, for example, you're trying to compare two arrays that are different sizes. Would it still be able to compare those two different arrays with different sizes? Like if you want to, let's say, just add a non, you cannot have you have to have them the same shape.
Mm-hmm.
But in JAX, would it be able to add it, if it's different sizes?
Yeah, good question. So and the question is in JAX, are you able to compare two different arrays? So I think there's maybe two separate questions here. One is if you're trying to JIT compile a function that has two different sized inputs and you have some operation that combines the arrays, will it be able to do that? And it will be able to JIT compile it, but it will only use the compiled version if both input arrays are the same shape. So if you run it once with an array of size 5 and 3, and then you run it again with arrays of size 6 and 3, it won't use the compiled version. There was like second part of your question that I kind of forgot.
If you add 5 and 3 together, will you still like?
Oh, like if you do a vectorized like addition.
Yeah, if you're vectorizing like a vectorized addition, like, can you do that with different shapes?
Yeah, I don't know. Let's see. JNP dot a range 10 plus JNP dot a range 11. I actually also don't know if the well, let's see what happens. Okay, we got a type error, so that's good. We might let's see if we do JNP dot sum, because no, okay, so JNP.sum only operates on one array, so we can't put in two different arrays. Okay, so it won't do that. That's sort of a weird edge case because the plus function is actually in Python. So even though like you can do plus on even though you can sum things, like you can do it uses a vectorized implementation of sum. I think in JAX it's not going to it's going to just use that implementation and not a JAX version of that. If you want to do summing in JAX, you got to do the JNP.sum, which requires one array as an input. Yeah, good question. All right. So the rest of this is these sort of useful higher order functions. So one is the jax.grad, so that'll automatically do differentiation for you, which, like I said before, can be helpful for when you're using like gradient-based like optimizers or MCMC methods or training neural networks. You can also do automatic vectorization with jax.vmap. So this is also kind of like a brain twisty kind of thing to think about, but it's very helpful when to think about like if you can basically replace a lot of for loops with actual like VMAP functions. So I'll let you read this through if you're curious. Okay, so for the rest of the time, I want you to work on this activity. Basically, we're going to assess JAX's performance on CPUs and GPUs, both running the JIT compilation step and not running the JIT compilation step. The way that you can access GPUs within the Colab notebook by just going to runtime, then change runtime type. So right now I'm on a GPU. There's also a TPU available right now, pretty cool. We'll go back to a CPU. The sort of annoying thing about this is that it will like terminate your current session. So any like variables that you have, you're gonna lose. This sort of makes the like actual like coding of this a little bit annoying, but yeah. So go through and run this profiling command as it instructs you on the CPU, on the GPU. Think about JIT compiling versus not JIT compiling, and interpret the trends you get. All right, so let's, I'm gonna give you 20 minutes and then I'll take 3 or 4 minutes at the end just to show you the answer. All right. Yes, the question is the Colab on the Code Astro repository. It should be on day 2, I think. Yeah, let me check where it is. Yeah, here we go. Yeah, right down here. All right. I'll just briefly go over what the plots that I ended up with look like, so you can understand some of the differences between these things. Okay, so here's the difference on a CPU with JIT compiling versus no JIT compiling. So you can see in general the sort of exponential growth of the time it takes to run this function when you have a larger and larger array, and the sort of like almost constant time difference between using the JIT compiled version and the not JIT compiled version. For the GPU, we see there's also a significant difference between using the JIT compiled version and not using the JIT compiled version. but there's a more constant amount of time that it takes with the array length. And this is because the GPU is able to run these very large computations basically in parallel. So up till the size limit of the GPU, you're not going to see increases in speed. At a certain point, once you get very, very large arrays, that even the GPU will start to have to do things in batches. And so you will ultimately start to see increases in the time it'll take to run everything. But for these very large arrays, million element arrays, we're still not seeing that overall increase. All right. Any thoughts or questions?
Your GPUs lower.
Yeah. Oh, that was the other thing I wanted to say. Thank you. So the question was, is it me or is the GPU slower? So initially the GPU is slower. So you can see that when you have small arrays, it takes actually less time to run it on a CPU than it does on a GPU. And that's because of the overheaded time it takes to actually like load the data onto the GPU. So distributing the data to the GPU so that it can actually be then performed, all these operations can be performed in parallel, takes some amount of overhead time. So this is also a good lesson in like when to use GPUs versus not use GPUs. When you have a small array, the CPU wins because you don't have that overhead time of loading the GPU. But when you have a larger array, and you start to see this exponential increase on CPUs, the GPU is going to win. Yeah, thanks for pointing that out. All right. Well, thanks everyone. Happy end of day 2 of Code Astro. We'll see you tomorrow.